Good morning, everyone. Welcome to our third press conference today. And we'll hear all about plastic litter, how it's transported, reaches the food chain, and what we can learn from it. We have three speakers today. The first one is Esperanza Huerta, who is a researcher at the El Colegio de la Frontera Sur in Mexico. And she's also a guest researcher at the, I actually can't pronounce this, Wageningen University in the Netherlands. And then we have Christian Schmidt, who is a researcher at the Helmholtz Center for Environmental Research in Germany. And finally, we'll hear from Lasse Sander, who is a researcher at the Alfred Wegener Institute in Germany as well. And I'll now hand over to our speakers.
Okay. Good morning, everybody, and thank you for being here present and interested in this topic. This work that I'm going to present is a work done together between Mexico, el Colegio de la Frontera Sur, and Wageningen University in the Netherlands. So I'm going to talk about, as you can see in the slide, about a problem that is occurring in the south of Mexico, but that can happen also in other parts in the world. This is about the modern Mayas that live in home gardens, and now because everybody we have television and the patterns of consumption have changed, so there is plastic. So I'm going to talk about this. Okay. So about plastic in the terrestrial ecosystem is not really known, or there is not too much information. Here I present some drawings in which they talk about this problem, how due to the industry, in the agriculture, in the right corner, you can see there is this mulch, plastic mulch, and then this was done and it is done in agriculture, but then the residues of this plastic, nobody knows what is happening. So there are problems inside of the soil due to the mismanagement of plastic. For instance, in agriculture, for instance, when there is not a good recollection of wastes, when there is a lot of wastes, and there are in the open areas like this deposit, that happened a lot. In Latin America, you can see it, and also here in 20 years ago or 30 years ago in Europe. And I have to say that one person produced 1 kilogram of waste per day. And from this kilogram, in average, 200 grams are plastics. Okay, so we found plastic inside the soil. That is an evidence. So, but we had a question: what happened with the soil organisms when there is plastic? So previously, we did a mesocosm experiment in Wageningen University, in which we saw that earthworms can in fact eat the plastic. They can transport the plastic inside the tunnels that they made inside the soil. They can transport the plastic inside their body and in their casts. The feces of the worms are rich in plastic. When on the surface there is plastic, the worms eat, and then they introduce the plastic inside, and in the cast there is plastic. And this plastic is concentrated. That means that there is more plastic in the cast of the worms than in the soil that is not eaten by the worms. And this is a very strong risk. And you can, if you want to know more about this, there are 2 papers that is already published on environmental science and technology and environmental pollution. Okay, so we did that in laboratory, and then we asked, okay, what we are going to find at the field at field conditions. So in Mexico, in the south part of Mexico, that is very well known because the Maya culture, the pyramids, the high biodiversity, you can see, well, there is a diversity of birds, mammals, but this in those places, in the natural reserve areas, they live persons, and these persons, they have problems of waste management, and because they have these problems, they burn their wastes, and they burn the plastic. Okay, so here you can see there is a common home garden. We worked in 10 home gardens, and you can see at the bottom of the photo, there is plastic, bottles of plastic there accumulated. So we selected 10 home gardens with the same economical conditions, and then we took samples. We took samples from the soil, took samples from the earthen cast. You can see in the middle of the photo, these like little things, black, are the earthen casts. And we quantified the plastic over the surface of the soil, the microplastics, and also we took chicken faces, because in the home gardens there are also animals, and then we took chicken faces and we also analyzed the chicken. In the photo, in the drawing on the right side, you can see there is gizzard with red underline and crop. So we opened the chicken and we saw if there is plastic inside of the chicken, in the gizzard and in the crop of the chickens. And yes, what we saw is that in fact the plastic goes through the food chain. After the plastic is burned, because then it is fragmented, it's in little pieces, that makes that it's incorporated in the soil. So we found plastic inside of the soil, we found plastic inside of the cast of the worms, and concentrated more amount than in the soil, and we found plastic in the chicken faces, we found plastic in the chicken, in the crop, and in the gizzard, macro and microplastic. And this is a very strong risk because humans eat gizzard, and not only in Mexico, around the world. In France, for instance, it is a culinaire broth, no? In the broth, in the bouillon, no? You eat gizzards. So chicken accumulate plastic in crop and gizzard. Soil and plastic debris in home gardens are the source, and humans eat gizzard. So this photo is just to show you can see the plastics, and because of the management, yeah, it can go through the food chain, and you can find it in the gizzard. There is a dish there. Mm-hmm. Oh, and that is, thank you. This is the presentation. Okay, now I'm going to put the other one. Mm-hmm.
Yeah, hello everybody. Welcome also from my side. The topic now is plastic in rivers. And my name is Christian Schmidt, and I would like to take the opportunity to acknowledge my co-authors that have contributed to that study. We'll start with the key points of our research. So we started from a commonly stated number. It's called 80% of plastic in the sea originates from land-based sources. But the transport mechanisms behind it are more or less unresolved. So we don't know, is it stormwater runoff? Is it rivers? Is it wind dispersal? And what we did, we hypothesized that rivers are a major contributor to plastic export from land to sea. And we did a meta-analysis. So we reviewed mainly existing data. We added a few data on our own. And what we can state is that plastic has been found in nearly every sample that was taken from a river. And what we also found is that the plastic loads, so the mass of plastic that is transported per time in a river, increases with increasing population in the river catchment. So rivers, large rivers with large catchments, with a lot of population, they transport a lot of plastic. And moreover, it's that large rivers seem to disproportionately, so they prefer to transport plastic compared to smaller rivers, because it might be that they simply are more suitable for transport. And to give you a number, so what we found is that the top 10 rivers that contributing most of the global plastic load, they make up like 90% of the entire load that enters the sea. So large rivers are important for the total load. And I will give you a few details in the other slides. So why rivers? So why should river be a source? So on the left, you see an example of the Amazon River basin. And what you see, it basically connects, so the outlet is on the right side to the Atlantic Ocean, and you see it basically connects all the little rivers that start in the mountains, connect the entire land to the sea. And for example, to give you some numbers, globally, every year, rivers discharge 6,000 cubic kilometers of fresh water into the ocean. And for example, the suspended sediment load as 13.5 billion tons per year. So these are known numbers. And the question is, how much plastic is coming with those rivers? And actually, we don't know exactly, but we are trying to find out how much it is. And what we found is that, so we divide our analysis into microplastics and macroplastics. That's a bit arbitrary. So commonly, the division is made by particle size of 5 millimeters. That's because 5 particles of 5 millimeters and below can be easily ingested by organisms, such as chickens, and larger particles not. That's why we make this difference. And of course, larger particles, they are transported differently than smaller particles. And so this is the result on the y-axis is the load. This is the mass per year, and we plotted it against a number that we called mismanaged plastic waste. That's based on a global data set on waste and also the plastic in it. And in 2015, Jambeck came up with a classification scheme. So they said, okay, a certain fraction of the plastic waste is mismanaged. And you see in the picture what it's meant. So properly managed waste that's collected and recycled or properly deposited, and mismanaged waste, this is the fraction of plastic waste. This is potentially available for transport by wind, by water, and whatever. And so what you can see, or what we calculated, let's go back one slide. So you see the range, so both is log-log scale, so the load in rivers varies over 10 orders of magnitude. So there are rivers with very high loads and rivers with very low loads. And to explore this a little bit further, we calculated something, it's called, or we call it the delivery ratio. So it's the ratio between the amount of plastic waste that is produced in a river catchment and the amount of plastic waste that is actually transported in a river. And you see the dashed line on top, this is 15%. So the maximum amount of plastic waste or mismanaged plastic waste that has been produced in a river catchment, the maximum rate that is transported is 15%. And you see also it's log scale, so it's over 6 orders of magnitude, so that most rivers, or many rivers, transport only very, very small fraction, like 10 to the power of -5, which means that only one particle of 100,000 particles is transported. And you see again, it's positively related to the amount of plastic waste that is produced, which means that larger rivers with high population, they tend to transport more of their plastic than smaller rivers. So smaller rivers seem to retain plastic somewhere in the system, while larger rivers transport it to the sea. And to conclude, I had it already at the beginning. So this disproportional contribution of those large rivers leads to the fact that the top 10 rivers export almost 90% of the global load. Then it would be proportional, like if the same fraction of waste would be transported in each rivers, then the top 10 rivers would only contribute 58%. This is proportional to the discharge that they contribute. And this means that if you would manage to reduce the load in these large contributing rivers by 50%, you would reduce the load into the sea by roughly 45%. And that's the point I want to make here. That's it already. Thank you for your attention. And next speaker.
Okay, hello. My name is Lasse Sander, and I am a postdoctoral research associate on the German island of Sylt. This is the northernmost tip of Germany. It's Denmark right across, and it's in the middle of the European Water and Sea. And I'd like to quickly acknowledge here that I was previously employed at the University of Copenhagen and at the Geological Survey, likewise in Copenhagen. And it was during that time that I conducted a bit of field work on a peninsula located in southwestern Denmark called Skellingen. And I will, for this press conference, cover the part that is what can we learn from plastic deposits, so plastic as a sediment in natural environments. And I prepared this short presentation called Marine Litter as a chronological marker in recent coastal deposits. And the background of this study is a learning context, so you can see a few people standing there on this beach and in the overwash fan. Those are students, and they were measuring DGPS transects to assess coastal change over time. And what you can see on the right-hand side, that is the modern beach. Where I'm standing taking these pictures is the so-called fore-dune, that is the Aeolian transport of sand from the beach onto a dune. And what you can see on the left-hand side is a so-called overwash fan, so it's a storm deposit. So at the occasion of high water event, you have water pouring or breaching the fore-dune ridge and the depositing deposits in the Blackberry environment. Now, the important point here is that the beaches are regularly cleaned by the local administration. The back barrier isn't. So there's a lot of plastic preserved there, and I started walking around and looking at it. So the main findings of this talk will be that plastic as a material has a chronological indication. There has been times where plastic wasn't around, and there's a time where plastic has been around at increasing amounts. And plastic as an object additionally contains information. So we can take a fragment of plastic, look at it, flip it around, and interpret what its function has been or still is, or if it's a fragment, how the whole thing may have looked like before. What's important here is that many plastic items contain mold dates, so we can know when they were produced, and we can retrieve additional information from number codes on them. But I focused on date prints today. So these date prints reveal the age of the deposit. And if we then compile a spatial record of these date prints, we can draw our conclusions on the extent and timing of the event deposition, so reconstruct storm events based on plastic that is contained in it. And I was quite surprised by that. It was very much a coincidence that I started to look at the plastic that was deposited there. So about the southern North Sea, I indicated here the position of the Skellingen Peninsula and the island of Sylt, where I currently live. And there's between 200 and 600 pieces of marine litter on 100 meters of shoreline in that area, so that is quite a lot. And 3/4 of those are plastic items. And the great advantage of plastic, of course, is that it's cheap, lightweight, durable, and that is our disadvantage as soon as it ends up in the natural environment. So what I indicated here is that plastic has been invented before the 1950s, but it hasn't really been around before the 1950s in commercial production. So the production took off around 1950s. But in this little box, you can see 3,500 pieces of plastic were found per square kilometer of ocean surface in the Sargasso Sea already in 1972. So the time period from the commercial introduction to the deposition in the natural environment is merely 20 years, and those are high amounts of plastic. And it only got worse since. So today we have a global production of 322 million tons per year. And the old plastic, of course, sticks around because it doesn't disintegrate entirely in the natural environment, so it only adds up. Now, what I did is that I went to these overwash deposits and picked out plastic pieces that were large enough to contain the date prints. So it's indicated in step 2 here. You usually have in the middle the age, the year of production, and around that the month of production. And I walked around and took spatially consistent, I took coordinates. So I had in the end X and Y coordinate and an age based on the date print contained on plastic items and compiled a spatial record. And next slide is the important point. I was quite surprised, came home and plotted those, plotted the spatial record and got something that looks like this. You have in the dashed and dotted and colored lines the actual extent of overwash deposition reconstructed from satellite images and aerial images. And this is the scientific sound way of reconstructing past storm events, or one of the possible ways of doing that. Now what you can see is that the dots from green to yellow to red represent the plastic dates that I recovered from it, and they reproduce a spatial pattern. So in the southernmost part, you can see there's a mix of date prints from the 1970s, late 1970s, 2014. The study was conducted in May 2015. Slightly on the side of that, there is a population of yellowish to light greenish samples. Those are the ones that were deposited in a storm event in the mid-1990s, and they stayed in place. So in this location, they show us that the fore-dune ridge has recovered since the breach of the fore-dune in the mid-1990s. So the plastic is still in place, the fore-dune is back, and we can sort of date the deposits based on the litter that is contained. If you move further to the north, there's less plastic. This is partly because of coastal reconstruction by the authorities. But we can see this inner part with the orange samples that is repeated breaching in around 2006 to 2008. And what happens is that we, in the aerial images and satellite images, only have time steps. So we can see something happens between, let's say, 2002 and 2008. And we have the plastic record sitting somewhere in between. So it adds up to the amount of information we can retrieve. And then in the furthermost part to the north, we have the red samples. That is an overwash event that had occurred before the new survey was made. So there were no aerial images yet. So there is now a layer of sand covering this area. So to conclude this, plastic items are very regularly found as fossils in recent coastal deposits. And this is the original background of the study that I tried to explain the passage of time to students. The usual way of dating deposits is a little abstract, and for undergraduate students, hard to grasp. But most of the students immediately understood the concept that you have deposits with plastic and those without. And those without are older from the time where there was no plastic around. Then the plastic preservation bears witness of the long standing of plastic pollution. So I recovered date prints for about 4 decades. And the date prints on the plastic items reveal the age and extent of event deposits, the overwash deposits. And then there is plastic surveys, or the potential that plastic surveys hold information that reveal anything about past coastal change. And I will present a post about this on Friday. So if you have questions, stop by, write, or ask now. Thank you.
Thank you very much for your presentations. We'll now open the floor for questions for all the 3 speakers. Would anyone here have any questions?
Thank you. Mariette Leroux, I'm with the Agence France Presse. I have a question for Esperanza. It's about the chickens. I wondered if you could be a bit more precise about how much plastic did you find, and what were the concentrations in the gizzards? And are those concentrations that are in any way dangerous for humans if they were to eat them?
Well, it's a very good question. I can answer this if I show the slide. If it's, okay, because I have there the amount. Okay, yeah, we found micro and macro plastics. In the gizzard, the size of the plastic that we found is from 1 millimeter to 11 millimeters. I'm giving the range. And the amount is from the micro, that is lower than 5 millimeters, is from 1 to 34. And that is bigger than 5 millimeters is from 2 to 120. This is the amount of particles. Yes. And about the second question, if it's dangerous for the humans, we don't know, because we didn't analyze the humans. We stopped with the chicken. Yeah. But yeah, it's very possible. I mean, that because we did an interview with the owners of the home gardens, and we asked how they cook the gizzard, and 70% of the persons don't clean by the inside, the gizzard, only by the outside. So that means that the risk that they are contaminated with plastic is very high.
Thanks. Jonathan Amos, BBC News. Question for Christian. Why is there such a large disparity between your numbers and Jenna Jambek's numbers?
The numbers are not that different. So when you sum up my numbers, you would end up in an annual load. I mean, it's pretty, yeah. So when you sum up these and extrapolate it to the globe, you end up with like 400,000 tons per year to about 4 million tons per year. You see the uncertainty is large because there's a lot of scatter in the data. So, and this is more or less in the same order of magnitude of Jambek's results, which was like between 8 and 12 million tons per year.
I think it was 4 to 12, wasn't it? Was it 4 to 12?
4 to 12, and we are a bit lower. So the tendency for rivers is a bit lower, and the reason for that, Jambek used a delivery ratio that ranged between 15% and 40%. And you see that the 15%, so their lower estimate is our max. So we don't see it in the data that it's really that much of the mismanaged plastic waste that is actually transported in rivers. So 15% is the extreme case, and most of rivers transport much less than this 15%. And you see it's log scale, so 10 to the power of -6 is only 1 part in a million that gets transported.
So can that difference be accounted for, I don't know, by wind, by other delivery mechanisms?
Yep. So we didn't look at other delivery mechanisms, and Jambake, they summed it up. So they assumed that's the whole potential that moves to the oceans. And of course, wind dispersal or direct stormwater runoff from coastal cities may contribute, but we don't know the numbers yet. I think with every study that comes out, we can constrain the numbers a bit more.
We have one question from the web stream.
So this question is from Albert Gerdes in KDM for Esperanza, and it is, are any measures being taken by local, regional or national authorities to prevent the use of plastic products? And are there any local or regional action groups or citizen initiatives to prevent the use of plastic?
Well, thank you for your question. As I told, these home gardens are in a reserve, in Los Petenes. Los Petenes is a reserve at the south of Mexico, so they have educational programs. They know that they have to separate the wastes, but they don't do it. I mean, they have the plastics there in the corner, as you saw in the photo, and then they burn it. So it's what they do. And I ask, why do you do that? Because I was doing the field work there, and then they say that yes, because they don't have another option. That was the answer. But the government, I also talked with one of the persons in charge in the Secretaría de Ecología, was ecology secretary in the Minister of Ecology in the state of Campeche, and they were very concerned, but they didn't do anything. I think there is a lot of politics behind, so it's difficult to have a solution, because I think this is a compromise between different parts, because for one side there is the companies that deliver the drinks. Well, fortunately this is glass, but the companies that deliver plastic bottles and that, I think they will be also responsible of taking their wastes back, because what they do is just there is a big facility of receiving plastic bottles and to drink, and in hot weather, well, they drink a lot of Coca-Cola, and I don't want to make commercials, but they do that. So the problem is that the wastes are there, as I saw in the photo. You can find 70 bottles per meter square, so it's really very high. And then even they know that it's a big problem. They don't do anything. So I passed information, but then I will try to pass more. But I think it's a problem with different factors and where different persons must be involved. Thank you.
Thank you very much. Are there any additional questions?
Liz Gallagher from Environmental Research Web. I've got a question for Christian. You talked about stopping plastic getting into the bigger rivers. What kind of ways would there be for doing that?
Good point. Tough point, by the way. So I think one way to do it is a proper waste management, and in general, and a better awareness that plastic is mobile in the environment. I can't talk for like other parts of the world, but in Germany, for example, we see it in our rivers in Leipzig. That a lot of plastic particles is not waste as such, but it's, for example, from building insulations. When these pieces of insulation are cutted at a construction site, it ends up in the runoff or in the wastewater system. And also municipal wastewater. Often many cities across Europe have combined sewers, which means that stormwater runoff and domestic wastewater is in one channel. And during a storm event, water of these combined sewers is directly discharged into the rivers. It's called combined sewer overflow. And this is, for example, a source of plastic in rivers for plastic particles that are in domestic waste. Or in domestic wastewater, sorry. And just to have a better awareness that these are sources for plastic, for example, packaging at construction sites, that would reduce the loads in Europe, for example. But of course, in developing countries, the story is a different one, because often these countries, they are missing a proper waste management and waste collection system. So if this would be established, that should reduce the loads drastically.
Sorry, we usually open the floor for questions from journalists, but if there are no more questions from journalists, I can let a couple of scientists ask questions. So, but it looks like there is one.
Luis Lidón from the Spanish news agency EFE. This is a question for Christian. I see here a figure about the total debris delivered to rivers. Is this the main amount, about the total amount that is going into the oceans?
Maybe not, because in our data set, we took all the sampling points that we could find in the literature, so it's not that many. So there's much more data on oceans than on rivers. And so there are sampling points in rivers that are somewhere inland. And of course, we can relate the loads that we find to the mismanaged plastic waste that occurs upstream of that site. But this is not necessarily the exact amount that goes into the sea, only when you consider it as infinite time. So because at a long time, everything that ends up in a river system should go to the ocean. But on a short time scale, of course, there's also retention in the river systems. Because plastic particles or larger particles, as you see in my intro slide, you see this is a shopping bag that gets stuck in a river at some sediment. So you have some temporary storage in the river system. But at the end, it should be that everything we measure in the river should ultimately end up in the ocean as long as the time scale is long enough.
Thank you very much. Are there any additional questions?
I have a question for Lasse. Do you have seen differences between plastics from the 70s and younger plastic, for example? So the degradation, is it different? Have you only tested macroparticles, or have you also analyzed for microparticles, for example? My name is Priska Henniken for Wiley.
Okay. I only looked at macroplastic, and it was only the plastic that was lying on the surface, so I did not dig into the sediment. And there is quite a difference, but not in the degree of decay. So you can find a plastic particle that looks totally new, but it's from the mid-1980s, and you can find some that looks really worn, and it's only 2 years old. And there's no direct correlation, and that's a little unlucky, but that's the way it is. But you find very pronounced changes in product design. So there was one item, for example, we dated based on that. So I found vintage advertisements. It was a detergent, and found them on eBay. And you could correlate the shape of the product as it was in that year with the shape it had in 1966. So that is a sample that is not in this collection. So product design changes. You find Nike Air Max in nice pinkish colors from the 80s. And then, of course, the design changes in PET bottles that occurred. There was this change from glass bottles to PET bottles, and maybe these glass bottles with the plastic, with the foamy labels that were around in the late 1980s, as I remember as a child. You find them still on the beach, so it's a travel back in time to our very recent archaeology of human use of plastics.
Thank you very much. Are there any additional questions from the journalists in the room? If not, we can have one question, I would say, from the scientists. Would any of you still like to ask a question?
I am coming from Croatia, and it is noticed sometimes rubbish, including plastic, comes from unknown areas. Do you have some plan to model origin of such rubbish, especially on the ocean or the sea? Some kind of monitoring, or just study sources, like in atmosphere, to make trajectory sources of air pollution.
Are you addressing all of us? For whom is the question? So I personally did not look at the sources of sediments only where they end up, but in the study I conducted, it was all marine-based. So a lot of it is fishing debris, so nets, fishing baskets, and those sort of things, detergents as you find them often on ships. But I didn't go in details about trying to uncipher the different sources. It could be an interesting exercise, but I did not do it at this point.
Well, I just put the slide in order to show there is a work made by Horston in 2017. I recommend to revise it. It's very recent, and they show how the plastic is in the aquatic system and also in the terrestrial system, and the sources about the industry, agriculture, and construction. Also, many particles are in the air. So I don't know if this can help to answer the question. There are different areas, no? The source is in the land, and then it goes to the ocean like this.
Maybe to add. So I don't remember the study exactly, but I'm sure there's a global ocean circulation model coupled to plastic inputs from land, and they modeled the accumulation in these garbage patches and other accumulation zones. So I think there are global models that couple ocean circulation with plastic debris.
Thank you very much. If there are no additional questions, we'll finish here. The next press conference is at 3:30, and it's on the grand finale of the Cassini mission to Saturn. I hope to see you all there. Thank you all very much for coming to this press conference. Thank you all very much for your brilliant talks. And yes, we'll finish here. Thank you.